do the following converge or diverge? And if the sequence or series converges, what does it converge to? If you see a question written like this, and you're looking at a series that you know is convergent, it's got to be one of two kinds of series. It's either geometric or telescoping. Those are the only kinds of series you are typically expected to find what those series converge to. Other series you can determine convergence, but like for example, if I asked you this question, does this series from n equals 1 to infinity of 1 over n cubed converge or diverge? We know it's going to be convergent. It's a convergent P series, but we don't know what it converges to, right? This series does converges, but we don't know, or at least we as students in this class don't know and are not expected to know that value. I don't know it either, but this one might be known. I have no idea if this value has actually been determined or not, but we don't know what it is. So all I'm trying to say is that if you see a question phrase like this where you're asked to find what the series converges to, you know if it's convergent, it had to have been geometric or telescoping because those are the only types of series we can determine what they converge to. Let's look at some examples. So let's say we were given this sequence here. Our a sub n is 4n squared plus 2n plus 1 over 7n cubed plus 5n plus 2. For a sequence, it's really, really easy to answer the question. You're just asking the question, what's the limit as n goes to infinity? So we want to find the limit as n goes to infinity of 4n squared plus 2n plus 1 over 7n cubed plus 5n plus 2. I would just say it's 0 because we know that the degree on top is lesser than the degree on the bottom. So I think it's fine to say it's 0. You might show more work by dividing everything by n cubed. But I think it's totally fine for a problem like this. Say, yeah, we know it's 0 because the degree on top is smaller than the degree on the bottom. On the other hand, if we were given some sequence like, I don't know, b sub n equal to, say, 4 to the n over n cubed, well, still the same answer in that for any sequence, we're determining convergence or divergence just by taking the limit as n goes to infinity. So we're going to take the limit as n goes to infinity of 4 to the n over n cubed. Now, in our hearts, we know this should diverge because we know that the numerator is going to overpower the denominator. But is it good enough to actually just say that? Probably not. You probably need to use L'Hopital's rule here to show that this actually is divergent. So using L'Hopital's rule 3 times, the first time we're going to get the limit as n goes to infinity of the derivative of 4 to the n is 4 to the n times the natural log of 4. On the bottom, we're going to get 3n squared. Do it again, you get the limit as n goes to infinity. The derivative of the top is another 4 to the n times natural log of 4 times the natural log of 4 that's already there over 6n. And finally, one more time, the limit as n goes to infinity of 4 to the n times natural log of 4 times natural log of 4 times natural log of 4, or natural log of 4 cubed over 6. And finally, oh, that thing is something where the numerator is still getting infinitely large and the denominator is 6. So we have infinity divided by 6, which is definitely infinity. So we would say this diverges. Let's look at some more interesting examples, meaning some examples with some series instead of some sums. So let's say we have the following series, the sum from n equals 2 to infinity of 3 to the n plus 1 over, sure, 2 to the 2n plus 3. Okay. I feel like I've written this in maybe not the most annoying way possible, but certainly in a more annoying way than is absolutely necessary here. So our job is to figure out what's going on. So I would feel like you can go about this two different ways. You can either try applying a test to determine convergence or divergence, or you could use the fact that you know that it's got to look like a thing that we're aware of if it converges. Meaning, if we think it's convergent, it's got to be geometric or telescoping. And it definitely doesn't look like it's telescoping. It definitely looks like it could be geometric because you've got things raised to the power with an n in it. So for me, I might just write out some terms just because I'm not sure. So I plug in 2, I get 3 to the third over 2 to the 4 plus 3 is 7. And then the next term, if I plug in 3, I'm going to get 3 to the fourth over 2 to the 6 plus 3 is 9. And just to confirm, the next term is going to be, I plug in n equal to 4, 3 to the fifth over 2 to the 2 times 4 plus 3 is 11. And yeah, it looks like every time we're multiplying by 3 on top and 2 squared on the bottom. That's one easy way to see that this is in fact a geometric series. Right, so I'm going to do one more thing before I do that, but another way to see that this is geometric and that the ratio is 3/4 is to rewrite this as the sum from n equals 2 to infinity. I'm going to break apart the n's and the not n's. So the top I'm going to write as 3 to the n times 3 to the 1. The bottom I'm going to write as 2 to the 2 to the n times 2 to the third. So we can rewrite this as the sum from n equals 2 to infinity of 3 over 8 times 3 over 4 to the nth power. And then it might be a little bit more obvious, at least the way it's written, that, oh yeah, this is for sure geometric. This converges because it's geometric and your ratio is less than 1 in absolute value. The absolute value of your ratio is less than 1. And then since the instruction said to find what this thing converges to, if it's convergent, we then have to say, okay, well, we know it's geometric, and the geometric series is going to converge to its first term divided by 1 minus its ratio. The first term we've already written down. It's right there. There's your first term. 3 cubed over 2 to the 7th power divided by 1 minus 3/4. This would be a great time to look at the question and ask yourself, did they tell me I needed to simplify my answer? No, you should really ask yourself, did they say I didn't need to simplify my answer? Generally, if they don't say anything, you should default on the side of simplifying. But what you should really do is leave your answer like that and then come back at the end of the test if you have time. Because simplifying that to whatever it's equal to nicely is not that important. It's maybe worth like a point. Whereas doing some other work that's more conceptual is probably worth more points. So I certainly wouldn't simplify this unless I had finished everything else and could then come back, okay, it's 3 to the third over 2 to the 7th divided by 1/4 is like multiplying by 2 squared over 1, and I can cancel a 2 there and get 3 cubed over 2 to the 5th, which is 27 over 32. But I don't feel like there's a lot of value there, right? You're not really showing you know anything about calculus and 21C, you showing you know how to multiply some fractions.
But if our instructor, like in our lecture, says it's acceptable to leave it like something like
Then
that,
you should leave it.
Okay.
Yeah, so definitely you should not simplify this unless you feel like you have to. So, but again, I would say, and you maybe should ask it like at the beginning of the test, like, do you expect us to simplify things like this or not? The downside is that is if you ask and they say yes, then you have to do it. Whereas if you don't ask and you don't know, you could kind of, well, I didn't know, so I don't know. You got to do what you got to do. I would, again, not simplify unless I had time at the end of my exam. Even if the instruction said to simplify fully, I would still not spend time doing that until after I attacked some of the more high value parts of your exam. Because definitely the simplifying there is not a high value piece, unless it's really easy for you to do really fast. If you can do it really easily, really fast, you should go ahead and do it. But if it's going to take you time to like work through how that, you should move on. All right, let's look at some more examples here. Sure. What have I got here? Oh yeah, yeah.
About the number 3,
Uh-huh.
why do you decide to use means of variance to do so?
Because So there's kind of two ways to go here. I would say the easiest way to always find what a convergent geometric series adds up to is it's always, always, always going to add up to whatever your first term is, which is 3 to the third over 2 to the seventh. Or if I plug in 2, 3 to the 2 plus 1 over 2 to the 4 plus 3, which is still that, divided by 1 minus a ratio. Some people do this stuff where you have to like you do all this kind of rewriting and it's really kind of a pain. It's really unnecessary unless your instructor says otherwise. But I think it's unnecessary. Let's look at something like the following. Sum from n equals 1 to infinity of, sure, I like something like this. 2n over 3n plus 4 to the nth power. Not geometric. Ooh, I might have asked a question I didn't mean to ask here. Let's make that 2 of 4. Sorry. 4n over 3n plus 4 to the nth power. So, what do I don't know. I don't know. I mean, I know what I want to do, but like, I want you guys to tell me what to do. What should I try to do? Yeah.
Should you separate or like flip the fraction up?
I could do that. That might help. I see something else though. I see an easier path. Well, in fact, what should I try first just to make sure? Yeah, test for divergence. Ooh, I don't know if I want to take that limit though. The limit as n goes to infinity of 4n over 3n plus 4 to the nth power seems kind of terrible. It's probably some e garbage that we don't want to deal with. So I will say this limit is probably not zero. And the way I'm seeing that without actually doing it is noticing that the insides here, as n gets larger, is going to be a number larger than 1. And you have a number that's bigger than 1 raised to a positive power, it's just going to get larger and larger. But even if it was smaller than 1, still probably would work out. But what I would actually point out here is instead of doing that, you could use the nth root test. So you could say, oh yeah, right, and the kind of giveaway here was that you had a power of n, you had that everything was raised to a power of n. And when you see that, doing the nth root test is a really easy thing to check. So we go, okay, the limit as n goes to infinity of the nth root of 4n over 3n plus 4 to the nth power. To the n and to the 1 over n cancel out, and you're left with the limit as n goes to infinity of 4n over 3n plus 4. And since you have a 4n to the first over a 3n to the first, that limit is going to be 4/3. That limit is larger than 1, which means we get divergence. On the other hand, if that had been a 2 in there, we would have gotten convergence because you have 2/3. And then I didn't want to ask it that way because I said you have to find what it adds up to if it's convergent. We cannot do it for that. So, yeah. To get one more in this vein, and then we'll move on. So, yeah, maybe. Let's say we want to find, let me write something down real quick here. Sorry, it's easier if I do it this way. Cool, that should work out. Yeah, all right. Sure, let's say we want to find the sum from n equals 0 to infinity of 2 over n squared plus 4n plus 3. This is a great question, if I do say so myself. So, intuition here. Do we think this? Let's show some thumbs. Thumbs up for if you think it converges. Thumbs down for if you think it diverges. Just based on the power we have. You think it's convergent. You think it's divergent. Or you can go in the middle if you're not sure. I definitely think it is convergent because essentially what I have is 1 over n squared, right? My power on top, I don't have any n, so I have a n to the 0, which is a 1. On the bottom, my n squared is the most important thing. The 4n and the 3 don't really matter. So that certainly looks like convergent. Now, I know why, I'm going to guess why some of you gave me a thumbs down and that said it was divergent, because you were thinking, well, if it's convergent, I have to be able to find out what it converges to. And you do, and we can. This is a telescoping series in disguise. Yeah.
Wait,
So
so, like, if we're asked to find what something converges to, are they gonna tell us? Wait, never mind.
okay. So I'll say it again though. If they give you a problem like this and they have told you, so I'll say it's possible, like the previous problem, they might make a mistake. Right. I made a mistake with the previous problem and accidentally asked something that I knew was going to convert, so I quickly changed something to that image. But if they've done their homework and written their test appropriately and didn't make any mistakes, if they say, tell me this thing either diverges or converges, and if you find that it converges, you have to tell me what it converges to, that means that saying this is convergent with along with that other piece of information means I know that this series is either geometric or telescoping. It's obviously not geometric, right? That's not something to be uncommon. Since it's not geometric, it must be telescoping. And if it's not written in a way that where it looks like it's telescoping, it probably means we need to use a 21B tool, partial fraction decomposition. Right, I know, terrible. So we're going to take our 2 over n squared plus 4n plus 3. I should point out. So this definitely converges. And you can show it converges with the limit comparison test. By limit comparison test with the sum of 1 over n squared from n equals 1 to infinity. That would certainly show convergence. Maybe, probably, no, yes, but you'd have to work for it. Because the thing is, with direct comparison, you have to say that that thing is strictly smaller than the other thing that's converging. And 2 over n squared plus 4n plus 3 probably is eventually less than 1 over n squared or 2 over n squared, but I don't want to work that hard. I know that the limit comparison test will do it for me, right? Especially if your thing that you're taking the sum of is a rational function, meaning powers of n over powers of n, limit comparison test will always work. And it's just, for me, I feel like it's easier to just kind of like, yes, it works, do it, right? The work here that I'm not showing, we're saying, yeah, the limit as n goes to infinity of 2 over n squared plus 4n plus 3 over 1 over n squared ends up being the limit as n goes to infinity of 2n squared over n squared plus 4n plus 3, which is 2. And since it's a non-zero, non-infinite number, we know that both series have the same behavior. And since this series is convergent, this series is also convergent. But really, I'm not going to show any of that work. What I'm really doing is saying, cool, I know in my head that's convergent by the limit comparison test. But since I have to find out what it converges to, it means it's either telescoping or geometric. And since I know it's not geometric, I know it's telescoping. So I'm going to just find out what it converges to using the telescoping thing and then be like, cool, it converged by that test. I'm not even going to write this test down over here, even though that's what I used to kind of make my initial guess about what was happening. Guess is probably not strong enough. My initial knowledge, right? I knew based on that limit comparison test, oh yeah, this is going to converge. So
are we still expecting to remember this partial fraction decomposition without reviewing?
yes. Maybe. I would expect you to know because I don't know. I would. And certainly, I mean, I don't think it's unreasonable to expect that. Now, right, 21C after the summer, when did you take 21B? Who knows? So maybe it's been a while since you talked about partial fraction decomposition, but it is not an unreasonable expectation that someone could actually what's it. It's more likely they would write it in a more obvious way. But I just wanted to make you aware that something like this could pop up. So let's do it. We're going to rewrite this as 2 over factor the bottom, n plus 3 times n plus 1. And then it's going to be a over n plus 1 plus b over n plus 3. And then we're going to take this equation and multiply both sides by the common denominator, n plus 3 times n plus 1. So if we multiply by n plus 3 times n plus 1 on both sides, we're going to end up with 2 on the left equal to a times n plus 3 plus b times n plus 1. Doing it the easy way, picking nice values of n, if I pick n equal to -3, I get 2 equal to a times 0 plus b times -2. In other words, b equals -1. -1, that's a -1. I'm sure you all can tell. Let me try writing it up again. There we go. Picking the other nice value, which is what? Right? I get 2 equal to a times positive 2 plus b times 0. So I get a equal to positive 1. Most of the time, it's going to work out where one of them is positive 1, one of them is negative 1. It could be positive 3 and negative 3, but they do have to be like the same numbers but opposite. They can't be like 2 and 5 or 3 and negative 7. They have to be opposite, otherwise things don't cancel out. So then we're going to rewrite our series from n equals 0 to infinity. Instead of using 2 over n squared plus 4n plus 3, we're going to write 1 over n plus 1 minus 1 over n plus 3. And now things are going to start to cancel out. So here's, yeah. So we start writing things out. I feel like this might not be precise enough for some people. We're going to get 1 over 1 minus 1/3 plus 1/2 minus 1/4 plus 1/3 minus 1/5 plus 1/4 minus 1/6, and so on and so on and so on. And then we can see the negative 1/3 canceling the positive 1/3, the negative 1/4 canceling the positive 1/4, the negative 1/5 would cancel out with the positive 1/5 that would show up over here, and so on and so on and so on. The negative 1/6 would cancel out with the positive 1/6 that would show up over there. So we're going to get 1 plus 1/2, which is 3/2. However, I imagine your instructor probably wants you to be a bit more precise about how you do this. Meaning, specifically for a telescoping sum, you probably should do the thing where you find the partial sum, the nth partial sum. So let's write out the nth partial sum because it's not that terrible. So instead, we're going to say that our nth partial sum from n equals 0 to capital N of 1 over n plus 1 minus 1 over n plus 3. Okay, here's something to remember. Whatever these factors differ by, in this case, they differ by how much? What's the difference between n plus 1 and n plus 3? 2. That's how many terms you're going to have adding up together. However much they differ by, you're going to have that many terms that don't cancel out, essentially. So what I'm really trying to say is you need at least that many in the beginning and at least that many in the end so that you kind of see what's going to happen and have the things that don't cancel out. So I'm going to write 3 terms on each side. So I'm going to have n equals 0. Okay, so I'm going to have 1 minus 1/3 plus 1/2 minus 1/4 plus 1/3 minus 1/5. Okay, I'm starting to see where the canceling is going to happen. And then to the very end, I need to go to not just capital N, but really capital N minus 2, capital N minus 1, and capital N. So for capital N minus 2, it's going to be, let's see, 1 over n minus 2 plus 1 is n minus 1. And n minus 2 plus 3 is n plus 1. And then for n minus 1, same deal. n minus 1 plus 1 is n. n minus 1 plus 3 is n minus 2. n plus 2. See, it's hard. Finally, the very last one, that's n minus 1. And then for the very last one, capital N, you just get 1 over capital N plus 1 minus 1 over capital N plus 3. Sorry for the lack of room there. Let me zoom in a bit so you all can see that a little bit better. So then we're going to say the negative 1/3 cancels with the 1/3. The negative 1/4 we cancel with the 1/4 there. The negative 1/5 we cancel with the 1/5 there. And then on the other side, the negative 1 over n plus 1 cancels with the positive 1 over n plus 1. And then there would have been a negative 1 over n plus 2 that would have canceled with that. And is that right? This is where nope. Nope. Yeah, this is where I kind of start to blow it. That shouldn't have canceled. There should have been a minus 1 over n here that cancels with that. This is still good. This is still good. So this ends up equaling 1 plus 1/2 minus 1 over n plus 2 minus 1 over n plus 3. Which kind of feels like a pain. I won't lie. And then finally, to find the actual sum from n equals 0 to infinity of 1 over n plus 1 minus 1 over n plus 3, it's going to be the limit as n goes to infinity of our Sn, which is going to equal the limit as n goes to infinity of this expression, which is clearly going to go to 1 plus 1/2. Because these parts go to 0. Would I do all that in an exam? I don't know. It feels like a lot of work. if it were me, even though this is probably the more right way of doing it, I'd probably do it this way. Be like, yeah, things cancel. The only thing you have to kind of think about in your head is like, do the things that are canceling at the end get smaller and smaller and smaller? The things at the end, right? The 1/n+2 and the 1/n+3 here, those terms that like don't cancel out, they do have to have a limit that goes to 0. Otherwise, this thing actually doesn't converge. On the other side of that, just to kind of point out one last thing, and then we'll finally talk about something not exactly this. You all should be aware that showing something like this, sum from n equals 2 to infinity of, which way do I want to go here? Sure. The natural log of n plus 1 minus the natural log of n. This is also telescoping, and it diverges. Because here, that thing you get at the end, like natural log of capital N plus 1 or whatever, when you take the limit of it, that limit is infinity. So that's how you deal. Okay, I feel like now that I said it, we should go ahead and do it. So let's just find the nth partial sum. So starting at 2, we get the natural log of 3 minus the natural log of 2. We'll do another term. Then we get the natural log of 4 minus the natural log of 3. We go all the way out to our n-1 term. We get the natural log of n minus the natural log of n-1. Finally, the last term, we get the natural log of n plus 1 minus the natural log of capital N. We get this canceling with that, this canceling with that, and then we have this canceling with that, this canceling with that. And so this becomes the negative natural log of 2 plus the natural log of n plus 1. And if we let n go to infinity, this is going to go to infinity, and you get divergence. That's what I meant by showing that. So not every telescoping sum is convergent. Many of them are, but some of them are not. All right. Let's ask some other questions. Does this series from n equals 1 to infinity, -1 to the n times n over n cubed plus 2 converge conditionally? Absolutely. Or diverge? What should I check first? Right. If you're asked about conditional versus absolute versus diverge, you should always look, well, I guess technically you should do the test for divergence first, just to make sure it's not a thing. But then you should really, right, this clearly is not going to diverge that way because the limit of that sequence is certainly 0. You should always check absolute convergence before conditional convergence, because if you find out that the series, like if this passes the alternating series test, you still have to then go check to make sure it didn't absolutely converge in the first place. So you should always check absolute convergence before showing alternating series test. So absolute convergence test. So we're going to take the sum from n equals 1 to infinity of the absolute value of -1 to the n times n over n cubed plus 2. And then I guess it's not, I should it's not really the absolute convergence test. It's just absolute convergence, right? There isn't like a test for absolute convergence because we're going to just test for absolute convergence by looking at the absolute value of our terms, which means we're really just dropping the alternating part. You're getting n over n cubed plus 2. And then you're going to show that this thing is convergent by whatever test you want that works. I think there are 2 valid options here: direct comparison or limit comparison. I would pick limit comparison, even though would totally work with direct comparison. It's too much thinking for me. Right? Like, even though I know that, okay, n over n cubed plus 2 is smaller than n over n cubed, which is equal to 1 over n squared, and we know the sum from n equals 1 to infinity of 1 over n squared is convergent. So this series converges by direct comparison, which means this series converges absolutely. I still would use limit comparison because that's just how my brain is wired. I would say, oh yeah, limit as n goes to infinity of my unknown sequence divided by my known sequence, because I know I'm comparing it against the sequence, the series for 1 over n squared, is going to give me a limit that's equal to 1. So I'm going to get n cubed over n cubed plus 2, which is equal to 1. And to me, that feels easier to think of. You might be different than me. That's all right. You can do it whichever way works best for you. But then what do we have to say? So we're going to say, great, the series converges absolutely. And we did that by one of the comparison test. By either direct or limit comparison test, whichever way you want to do it. It's probably a good idea on an exam to say which test you are showing the thing you have shown. That's usually an expectation. Otherwise, someone might look at your work and be like, well, I don't know what they're really trying to do here. Like they're taking some limits, but are they doing limit comparison? Are they using ratio test, right? Like it's good to say what you're doing so that it makes it more obvious. Sure. What else have we got here? Let's move along from this. I know there's a lot. So, we should do. Yeah, yeah. Okay, I got. Just thought of something else we should do.
If we estimation,
Like estimating.
uh,
I think like estimating some series with some number of terms.
yeah, well, estimating to like a certain like error.
Right. Yes. Let me. In fact, I had something. Where'd you go? Yes, I've got. Yeah. Let's look at this example that I have already pulled up. So let's say we want to use the first 3 terms of the Maclaurin series for the following functions. So use the first 3 terms of a known Maclaurin series. Sorry, let me write this. I apologize. Let me try that again. Sorry. Use the first 3 terms of a known Maclaurin series to estimate the following. And what do I have here? Give a bound for the error of our estimate. We'll start with something relatively easy. Let's say we want to deal with, where'd you go here? Let's say our first one is going to be 1 divided by the square root of e. Which feels like it might not feel like super obvious what Maclaurin series is using. Well, I see an e. In fact, I see an e to the negative 1/2. So the Maclaurin series I'm thinking about using is the Maclaurin series for e to the x. I know that e to the x is equal to the sum from n equals 0 to infinity of x to the n over n factorial. Or if you like, it's going to be 1 plus x squared over 2 plus x cubed over 3 factorial, and so on and so on and so on. So if we're using the first 3 terms to estimate this particular value here, this is one thing here. I just want to make sure I'm not making some silly mistake here. Apologies. Right, yeah. So we're going to say that e to the negative 1/2 is going to be approximately equal to, well, I'm just using the first 3 terms, right? So I'm using these 3 terms. So I'm going to get 1 plus negative 1/2 plus negative 1/2 squared over 2. And that's my estimate, which we could simplify. That's going to be, let's see, 1 minus 1/2 plus 1/4 divided by 2 is 1/8. So we have 8/8 minus 4/8 plus 1/8 is 5/8. How are we going to figure out what a bound for the error is? Well, the first question whenever you're asked an error question, the first question you should ask yourself is my series alternating or not? Is this series alternating? Good, that's a good question. Is this series alternating? Well, which series am I talking about? The series for e to the x or the series for e to the negative 1/2? Oh, the series for e to the negative 1/2 is alternating. So the problem here is if you actually wrote out what e to the negative 1/2 was equal to fully, it'd be 1 plus negative 1/2 plus negative 1/2 squared over 2 plus negative 1/2 cubed over 6 plus negative 1/2 cubed to the fourth over 24, and so on, so on, and so on. And here is our estimate, and here's our remainder. And since this series is alternating, right, it's 1 minus a half plus a thing, minus a thing, plus a thing, right? It is alternating. And so by I forget what the name of it is, the alternating series estimate, remain, whatever the name of that thing is. The way you estimate the error of an alternating series is it's the absolute value of the first term of your remainder. So our error is going to be less than or equal to the absolute value of negative 1/2 cubed over 3 factorial, which is 1 over 48. But it does bear, we have to recognize that it is alternating. And so if you have a negative number getting raised to a power that is even and then odd and then even and then odd, that's going to make our terms change signs every time. On the other hand, what if we asked the same question, but said we want to estimate the square root of e? Well, now the square root of e is e to the positive 1/2, and we are not in such a fortunate situation. We're going to get 1 plus 1/2 plus 1/2 squared over 2 factorial plus 1/2 to the third over 3 factorial plus 1/2 to the fourth over 4 factorial, and so on and so on and so on. And even though I know I'm answering more than they asked for, but I think it's worth writing this out. Here's our estimate. So we're going to say that e to the 1/2 is approximately 1 plus 1/2 plus 1/4 over 2 is 1/8. That's going to be 8/8 plus 4/8 plus 1/8, which is 13/8. Here's our remainder. And here, our remainder is, our series is not alternating. So we have to do the other thing where you use like the Taylor's remainder formula. Again, the names, I hate the names for these things. Like, we're going to use that formula. So here's what we're going to say. We're going to say that we know that the remainder after the first n terms is going to be less than or equal to the absolute value of and it's essentially the next term with a little bit more, right? It's your next derivative, your n plus 1 derivative, evaluated at your value you're never going to find, multiplied by x minus 0, whatever your center is, to the n plus 1 power, divided by n plus 1 factorial. And that's as a function of x. So in this case, here's what we've got. We're going to have that, well, we are using the first, here's a good question. What's my n for this example? If I want to use the first 3 terms, my n is 2. Because where do we start at? N equals 0, n equals 1, n equals 2. So it's always like 1 less. But then, so essentially we're saying our R2 of, and we're plugging in what value for x? Plugging in 1/2, right? Because e to the x is the thing that's going to end up with 1/2 plugged in, is going to be less than or equal to your n plus 1 derivative at z times your 1/2 to the n plus 1 power. I should have written 3 there. Sorry, I didn't. Divided by 3 factorial. The only thing that's left to figure out is what to do with this here. Well, if you remember, our function was e to the x, and any derivative, even our third derivative, is going to equal e to the x. So we're going to say that this part here this third derivative of z, which is e to the z, we have to find a bound for that. But we are limited in where z gets to live. Z itself, which we don't know, has to live between your center and your x value. So here's the thing that's kind of silly. And I'm looking at my notes. Yeah, cool. So the problem here is you're trying to say, okay, what's the biggest this can be if z is between 0 and 1/2? Well, e to the x is an increasing function, so it's going to be the larger value. So this is for sure less than or equal to e to the 1/2. Right, how annoying. Here's what we almost always do. We just find the next biggest integer. So square root of e is approximately the square root of 2.7. Is that bigger than or smaller than 1? Bigger than 1, for sure. Is it bigger than or smaller than 2? Smaller than 2 because it's less than the square root of 4. Right, so since this is less than the square root of 4, which is equal to 2, I'm going to say that this part here is bounded by 2, which is a pretty standard way of doing this. You just find the next biggest integer that's bigger than or equal to whatever that thing is bounded by. Technically, you could do something silly and write square root of e here, but it feels really, really, really weird to be using the thing you're approximating to then bound your other thing, right? The whole point of this problem was to estimate the square root of e in the first place. It seems weird to be using that here. So, I mean, I guess you could use 13/8 if you want to, but let's go ahead and write this out. This is going to be less than or equal to 2 times 1/2 cubed over 6, which ends up equaling, see, 2 1/4 divided by 6, 1 over 24. Yeah. Yes. Right. So we're finding the remainder after using the first n equals 0, n equals 1, n equals 2 terms. So we're starting at n equals 2, and our formula says it's the n plus 1, so in this case, the third derivative, evaluated at some point in between, right? And z has to live between x and c, your x value center. So z here is living between our center, which is 0, and our x value, which is 1/2. Or we're plugging, right? I should back up a little bit. The whole way we got this was by taking the Taylor series, the Maclaurin series for e to the x, and then substituting in x equal to 1/2. So our center is 0 because we were told it was 0 because the Maclaurin series. Our x value is 1/2 because that's what we have to plug in to estimate the thing we're trying to estimate into the Maclaurin series that we figured out. And then what we're saying here is that this formula tells us that our remainder is, I suppose I've written this somewhat annoyingly wrong. Not really, but kind of. Technically, I should be saying the remainder is equal to this, and then this is bounded by whatever this is bounded by. So a more correct way of writing this would have been to say the following. The remainder after the first 0, 1, 2 terms, plugging in x equal to 1/2 is equal to my third derivative of z times my 1/2 to the third divided by my 3 factorial. And then we're going to say, I don't know what that is exactly because I don't know what z value I actually have to plug in, but for sure that's going to be less than or equal to, well, since my third derivative is e to the x, e to the x is increasing, so I know if I'm between 0 and 1/2, the biggest possible value is e to the 1/2. We don't know what that is, so we're going to just go up a little higher and say, well, I know e to the 1/2 is less than 2. So this is less than or equal to 2 times 1/2 cubed over 3 factorial, which is 1 over 24.